Okay, the video of the solutions for the derivative part of the review for Math 1100 for the final exam. These first four pretty basic differentiation problems just using the power rule. Differentiate means to find y prime or dy dx. So remember the power rule, the exponent just comes down in front to multiply. So the negative 5 is going to come down in front and multiply with the 5/3, making negative 25 thirds. And you decrease the exponent. What I would suggest in question 2 is to rewrite the expression. Now with rational exponents, it's the same rule. So this 1/5 is just going to come down in front and multiply the coefficient. So the 1/5 times 4/3 is negative 4/15. And then you subtract 1 for the exponent. So it becomes negative 4/5. On question 4, I would suggest a rewrite of the equation beforehand. So y equals negative 1/2 times x to the 2/5. And then this becomes all like question 3. The 2/5 here is going to come down and multiply in front of the coefficient. So 2/5 times 1/2 is 2/10, which is 1/5. So we have negative 1/5 times x to the negative 3/5. Question 5, from section 2.5, we were introduced to the chain rule. Chain rule involves taking the derivative when you have an inside and an outside function. Chain rule says you start with the outside function. So we have an exponent that's just going to come down and multiply in front. So we have negative 25. At this point, we don't do anything to the inside function. We decrease 1 from the power. Now, once we've done the outside function, we take the derivative of the inside function, which is 10x. And then we can multiply here, get negative 250 x. Question 6 is an application of the product rule with the chain rule. So what I mean product rule, we have one function here we could call f and another one g. So y prime, the product rule says f prime times g plus g prime times f. That's the rule I'm going to follow on this one. So y prime equals f prime times g plus g prime. Now g prime here is going to involve a chain rule, so we've got the outside part multiplied by the derivative of the inside. This whole thing is just g prime. What a lot of students forget is after doing that, you still need to multiply it by f. So let's just double check. We've got f prime times g plus g prime times f. So that's the whole of product rule with chain rule. The rest of this problem is just rewriting things to simplify it. So with this first part, not much we can do at this point. But here we can do the 4 and the negative 6x squared to actually make minus 24x squared instead of plus, so minus 24x squared Now if we look at the left side of this and the right side of this and factor out any common factors, 8x could be a common factor, and negative 2x cubed minus 3 is a common factor, and both sides have at least 3 of them, so that's how many I'm going to take out from each side. Now if I factor this from that, all that's left is a negative 2x cubed minus 3. If I take this from that side there, I'm left with a minus 3x and then I'm left with the 4x cubed or 4x squared plus 1. And then combining like terms, this is going to give me negative 12x cubed, and that negative 2x cubed is negative 14x cubed minus 3x minus 3. Okay, question 7, the rule we're using here is the derivative with respect to x of e to the u is e to the u times the derivative of u. That's the rule we're going to use here. So y prime is e to the u, but then we need to multiply it by du, which is 20x to the 4th. So we've got 20x to the 4th times e to the 4x to the 5th. The rule we're going to use here on number 8 is the derivative with respect to x of the natural log of u is 1 over u times du. That's the rule we use for derivatives as natural logs. But one thing that's very helpful with natural logs is to use properties of logarithms first. I've noticed we've got a product there, 4 times x to the 5th. So we can actually separate that. And then another property is we can move that exponent in front of the natural log. So this is what we're actually going to differentiate right here. Natural log of 4 plus 5x plus 5 times the natural log of x. We need to take the derivative of that. Now this first one here, natural log of 4. Natural log of 4 is just a number, and the derivative of a number is just 0. So that derivative becomes 0 here. 5 is just a coefficient, and then the derivative of natural log of x is just 1 over x. So the derivative is 5 over x. Okay, now number 9. Before trying to take a derivative of this one, it's going to be definitely most helpful to expand this logarithm. So I notice I've got an exponent there I could move down in front. And then since you're taking the natural log of a quotient, you can expand that using subtraction. So 2 times the natural log of the numerator minus 2. And the reason I'm using 2's here is because I had a 2 in front there. 2 times the natural log of the denominator and then I can move that exponent down in front to multiply with that 2. So we're going to have 4 times the natural log of x minus 2 times the natural log. Now I don't want you to get confused here. A lot of students will stop thinking that they've done something. They have, you know, you've separated the logarithm and expanded it, but we haven't taken derivative yet. We still need to use laws of differentiation. So y prime, if we're looking here, the 4 is just a coefficient, and the derivative of natural log of x is 1 over x. Here the 2 is a coefficient, so that stays 2, and the derivative of natural log of 3x to the 5th plus 5 is 1 over 3x to the 5th plus 5, and then we multiply it by the derivative of 3x to the 5th plus 5, which is 15x to the 4th. we have 4 over x, whoops, minus 30x to the 4th over 3x to the 5th plus 5. Number 10 is going to be an example or an application of the quotient rule. We have the bottom function multiplied by the derivative of the top function. This is a chain rule. So there's the bottom function multiplied by the derivative of the top function minus the top function multiplied by the derivative of the bottom function all over the bottom function squared. This is the quotient rule. Typically at this point, you just start simplifying where you can. In the numerator, let's see, there's a common factor in the numerator. If we look at that minus sign there, separating the numerator into a left and a right side, the left and right side both have an e to the x to the 4th, and also at least an x cubed in common as a common factor. So that would leave x to the 5th plus 3 multiplied by 4x, rather multiplied by 4. And then on the right side of the numerator, we'd have 5x over x to the 5th plus 3 squared. And then inside the numerator there, just simplifying, combining a few like terms, we would get 4x to the 5th minus 5x plus 12 x to the 5th plus 3 squared. Question 11, using implicit differentiation to find dy dx. Derivative of 4x is 4. The derivative of negative 2y is negative 2 dy dx. Recall implicit differentiation. When you take the derivative in terms of x of an expression y, then you need that dy dx as part of the chain rule. And then the derivative of 3y cubed is 9y squared. And again, we're taking the derivative with respect to x of an expression in y. So we need another dy dx. If you factor out a dy dx on the right side, then you can get dy dx by itself by dividing by this expression. So we'd have dy dx equals 4 divided by negative 2 plus 9y squared. Okay, we need to write an equation in slope-intercept form. Slope-intercept form, remember, is y equals mx plus b. So the most important part there is the slope. The slope comes from the derivative once we plug in a particular x value. So first task is to find y prime. The derivative of natural log is 1 over that expression multiplied by the derivative of that expression. So now we need the slope at that point. So y prime at x equals 1, and we choose x equals 1 because right there is 3 over 3 plus 2, which is 3/5. So we know the slope. We know the slope is 3/5. So now in order to use y equals mx plus b, they didn't give us b, which is the y-intercept, but they did give us a y and an x, and now we found m. We know all three of those values. y is here, natural log of 5, so natural log of 5 equals m, which is 3/5, times x plus b. So this is y equals mx plus b. That's all we're doing here. So we just need to get b by itself by subtracting. So natural log of 5 minus 3/5 is equal to b. So that's our y-intercept. So we know the equation now is y equals mx plus b. Same story here on 13. We need to find the derivative. And then find the value of the derivative at the x value, in this case at x equals -1. So -1 squared is 1, 1 times -3 is -3, -3 minus 8 is -11, and that's your m value. So we've got x and y, so y equals mx plus b. So we have 3 equals 11 plus b, which means b equals -8. So the equation is y equals -11 x minus 8. Okay, 2.8, related rates problem. We've got a wall, and then a 15-foot ladder is resting against that wall. Initially, the bottom of the ladder is 10 feet, and the bottom of the ladder is being pushed at a rate of 1/4 feet per second. Now, what I'm initially noticing is we've got a right triangle here, so I'm going to call this A, B, and C. And a related rate problem. In order to find a rate is a rate of change or a velocity. So here's a velocity right here, and that's the rate of change of A. So the rate of change of A is derivative of A with respect to time. So dA dt equals -1/4. And the reason I call it -1/4 is because it's moving in this direction. It's actually going towards the wall, and that's just the way velocity works. It's moving towards its negative velocity. If it's moving away, it's positive velocity. So anyway, we've got dA over dt is 1/4 feet per second. What they're asking for is how fast is the top of the ladder moving up the wall. So the top of the ladder here moving up that way means that this whole length from here to here is changing, so that means that we're trying to find not the value of b, we're trying to find the rate of change of b. So what they're asking us to find is dB over dt. When dA dt equals -1/4. Now, it says how fast the top of the ladder moving up the wall 12 seconds after we start pushing. So we got to think about this. Initially, from here to here, there was a distance of 10 feet. 12 seconds after we start pushing, what's that distance change to? Well, it's 1/4 feet per second. So 12 seconds of 1/4 of a foot per second means it's changed 3 feet. So after 12 seconds, what's actually happened here, I'm going to redraw the problem. The base of the ladder's gotten a little bit closer. and the distance from there to there is now only 7 because it's moved 3 feet. So we've got A, B, C, dA dt is still negative 1/4 feet per second. And we're trying to find dB dt. So after that 12-second mark, we still have a 15-foot ladder. A is 7, so we have a squared plus b squared equals c squared. We've got 7 squared plus b squared equals 15 squared. So that's 49 plus b squared equals 225. Let's see, 225, if we take away 49, that's going to be 176. Better just double check that. Yeah, 176. So b squared equals 176. So b is equal to the square root of 176. The reason we need the values of b there is now to find a rate of change dB dt. We go back. And c squared I'm going to change to 225 because c is always 15. The length of the ladder isn't changing. But a and b are changing, so I can't plug any values in for them yet. If I take a derivative with respect to time, I'm going to get 2a dA dt plus 2b dB dt equals 0. And now I can solve this equation for dB dt. By plugging in values, known values. For example, I know that a equals 7. So I'm running out of room here. I'm going to have to come over here. So 2 times a times dA dt plus 2 times b times dB dt equals 0. So if I move this term to the right side, that's going to be positive 7/2. And then I can divide by this term here, divided by 2 square roots of 176. And that's dB dt, and we can turn that into a decimal. So 7/2 divided by 2 times the square root of 176 is 0.132. Feet per second. So just going back over this problem, this is an example of implicit differentiation. So going back here, for example, to this step, the derivative of a squared is 2a, but we needed to do dA dt because remember we're taking the derivative with respect to time, and the variables don't match. The derivative of a with respect to time is dA dt. And the reason, again, I perhaps should have mentioned this at the onset of the problem. The reason we knew, or I knew, to call this derivative, for example, dA, or the derivative of a, was because it's a rate of change. A is changing, the base of the ladder is moving towards the wall, so that's a rate of change, so that's a derivative. But how do I know it was with respect to time? Well, it's because the rate was given in terms of feet per second, so it's in terms of time right there. So the way that rate was set up is the number of feet are changing, and time is changing, so it's the rate of change of feet, which is right there, dA, that's the distance from the wall, over the rate of change of time, which is dt. So we knew it was going to be the rate of change with respect to time. And so again, going back over here, if you had to take the derivative of a squared, it is 2a, but because the variables there don't match, this is implicit differentiation. So 2a dA dt. And the same thing here. Derivative of b squared is 2b times db dt. Okay, question 15 is another example of a related rates problem. Because we've been given a rate right here, the radius is increasing. And I want to find how fast the volume is increasing. Increasing means the volume is changing, so that's a rate of change. And the volume of a sphere is related to the radius. So these two rates are going to be related, hence related rate. Now the volume of a sphere is 4/3 pi r cubed. We've been asked to find the rate of change of volume, and so that's dv, but is it dv over dr, is it dv over dx, is it dv over dt? How do you tell? Well, the given rate is in terms of second, so we know it's going to be dv over dt. It's a respect to time. So find dv dt when the radius equals 8 and the rate of change of the radius with respect to time equals 4. So using those two values, find dv dt. Well, this is a simple differentiation problem. The derivative of v with respect to time is just the derivative of that expression. So the exponent 3 is going to drop down and multiply in front of the coefficient, in which case the 3's would cancel, so it's 4 pi r squared. And this is where a lot of students forget something very important on a problem like this. This is implicit differentiation, because we're taking the derivative with respect to time, but this is in terms of r, so we need dr dt, which we have right there, is 4. So 4 times pi times the radius, which in this case is 8 squared, times dr dt is 4 pi times 64 times 4. So we need to know 64 times 4 times 4, and that's 1024. Now this is rate of change of a volume, and volume is in cubic units, so this is centimeters cubed per second. Alright, we've finished problem number 16 several times in this course already. We've got some kind of an existing stone wall, and on that stone wall a rancher is going to build a corral or a pen using only 3 sides. So we just need to know what kind of dimensions would yield a maximum area, or largest possible area. So x would be the 2 sides. The width there could be y. Now it says there's 400 feet of fencing available. That would be the perimeter. So from here all the way around, measuring around, is 400 feet of fencing. So 400 would be the 2 sides, which is 2x, plus that middle part y. So that's given information, but it says it wants us to have the largest possible area. The area of this rectangular pig pen, the area of the inside, is just a rectangle, and the area of a rectangle's length times width. Now it says they want to give us the largest possible area. That's called maximizing. Maximizing, find the maximum this, find the minimum that. We talked a lot about that in this course. That's an example of finding a first derivative and setting it equal to 0. But we can't differentiate an expression x times y unless it's in terms of the same variable. So what we need to do is make a simple substitution here. If for example, we took this expression here and got y by itself, that means y could be 400 minus 2x, and then if we substituted that in for y right there, we could get a equals x times 400 minus 2x, which means the area is negative 2x squared plus 400x. So then the derivative is pretty simple, 4x plus 400. Now if we set that equal to 0 and solve it, we would get x equals 100. Now we need to test that that really is a maximum value, and the way that we test that is the first derivative test, which we learned about in Unit 2. We have the value that makes the derivative 0, and we plug in test points on either side. So I'm going to plug in a test point of 1 and a test point of 101 into the first derivative and see what happens. If I plug in a 1 right here into the first derivative, I get a positive value. If I plug in a 101, I get a negative value. And again, it's really important to remember what this means. This plus sign right here means that on the left side of 100, the graph is increasing. The negative sign on the right side of the 100 means the graph is decreasing right here. So we've got an increasing and then it decreases, which means when x equals 100, we have a maximum value. And which is what we wanted. We wanted the largest possible area. X equals 100 gives us the dimensions that give us a maximum area. So x equals 100, 100. There's only 400 feet of fencing available, so 100 plus 100 is 200, leaving 200 feet available for that side. So the dimensions is 100 by 200. Okay, maximum profit. This is another key word, maximum profit. To find the maximum this or the minimum that, remember we need to find a derivative, set it equal to 0. So we need to find a profit function. Profit is revenue minus cost. We've been given cost, but there was no revenue function, but we were given price. And if you recall, price, this is lowercase p, not uppercase p for profit, but price, rather, let me rewrite this. Revenue here, let me do it here. Revenue is equal to x times p for price. So this is x times 36 minus 4x. So that's negative 4x squared. So that's a revenue function right there. So now we could write profit as revenue minus cost. So this is revenue minus cost. So simplifying, combining like terms. Actually, let's combine like terms. So negative 4x squared minus 2x squared is negative 6x squared plus 36x minus 6. That's profit. The derivative then would be negative 12x plus 36. If we set that equal to 0 and solve it, we get x equals 3. Remember, x is number of units. I've seen several students here stop thinking that this is the answer, but it says what price yields a maximum profit. X is just number of units, and first we need to decide if that's even a maximum. So we do the first derivative test. Plug in test values on either side. So I'm going to plug in an x value of 1 and an x value of 4 into the first derivative. If I plug in a 1 right there, I get a positive value. If I plug in a 4, I get a negative value. So we've got increasing to decreasing, which is a maximum. But the price that yields that maximum profit, you need to plug the 3 in right here. 4 times 3 is 12. 36 minus 12 is 24. So the price is $24. If I set the price according to this model here with that cost and demand, then the maximum price, or the price they would want to have or set to yield the maximum profit, would be $24. When the profit's maximized, the average cost, average cost is cost divided by x. So this is 2x squared plus 6 over x. When the profit is maximized, we have an x value of 3, so all we got to do is plug in a 3 there. So 3 squared is 9, 9 times 2 is 18, 18 plus 6 is 24 over 3. So the average cost is $8 a unit. First partial derivatives. This is different than implicit differentiation. This is finding derivatives in 3 dimensions. So we need to find a derivative with respect to the x-axis and then a derivative with respect to the y-axis. So the first derivative with respect to the x-axis treats x as a variable and y just as a number. So pretty much just as a coefficient. So here we're going to have, for example, 3x squared, the derivative is 6x. And then y cubed we can think of as a coefficient. The derivative of 4x with respect to x is 4. The derivative of this, 7y cubed x. And again, we're thinking since y cubed is just a coefficient, the derivative of a coefficient times x is just that coefficient. And then the derivative of 3 is 0. Now doing the same thing, the partial derivative with respect to y, now we treat x as a coefficient, and we're taking the derivative of y where y is the variable, so now this 3 is going to come down and multiply that coefficient, so we're going to have 3 times 3 is 9, x squared, y squared, 4x, remember x is just numbers now, so 4x is a constant, the derivative of the constant is 0, and then 7y cubed would be negative 21. So matter of fact, I'm just going to call that minus instead of plus. Minus 21 y squared x. And then the derivative of a constant there is 0. Okay. Now seeing an application of several different things we've learned regarding applications of derivatives, intervals of increase, decrease, concavity, inflection points, critical values, all sorts of things here. The relative extrema, let's start there. Relative extrema come from the first derivative. And setting it equal to 0. I'm just factoring there. So know that x equals 0 and x equals negative 4/3. So those are critical numbers. Place those on a number line and test values in between. So we could test, for example, I'm going to test a positive 1. I'm going to test a negative 1, and I'm going to test a negative 2, all into this first derivative right here. So starting on the furthest left, if I plug in a negative 2, I'm going to get a negative 4 times negative 2, that's positive 8, so that gave me a positive value. If I plug in a negative 1, I'm going to get negative 2 times 1, that's a negative value, so I'm going to negative, and if I plug in a positive 1, I'm going to get a 2 times 7, that's a positive value. So this tells me that it's increasing. Anywhere I see a plus sign there, the function is increasing. So the function is increasing from negative infinity to negative 4/3, and it's increasing from 0 to infinity. Also tells me that the function is decreasing from negative 4/3 to 0. Now anytime we change from increasing to decreasing or decreasing to increasing, we have maximums or minimums, we have extrema. So increasing to decreasing would be a relative max at x equals -4/3. Now I'll go back in a second and find the y value. And we have a relative min when the function switches from decreasing to increasing at the point 0, comma something. Now those are just x values. To find the y values that match those, we need to go to the original function and plug those into the original function. So if you plug in a 0 into the original function, y would be 0. If you plug in a -4/3 into the original function for all the x's, I'm meaning the original function here. If you plug in a -4/3, I'm going to go to a decimal here because it's going to be easier to graph decimals anyway. That's going to be about 2.04. So that's all the stuff we can gain from doing a first derivative. Now, going to the second derivative, that's going to help us find inflection points and concavity. So that's going to be 12x plus 8. Now, if we set that equal to 0, subtract 8 divided by 12, we're going to get x equals -8/12, or -2/3. So, doing a similar test for concavity that we did for increasing or decreasing. Got to plug in test values on either side, so we can plug in -2/3, we could plug in a -1, for example, and we could plug in a 0 into the second derivative. Anytime you're doing test points, you test those in the derivative, in this case the second derivative. So -1 in the derivative gives me -4. If I plug in a 0, that's going to give me a +8. So the negative means concave down from -infinity to -2/3. It's concave up from -2/3 to infinity. And anytime we switch concavity, that's an inflection point. So we know there's a point of inflection when the x value is 2/3. If you plug, now since we're actually talking about a point on the graph, this isn't a test point anymore, so it doesn't go in the derivative. This is an actual point on the graph. Plug that back into the original function, and since we're going to be graphing this, I'm going to use decimals. That's going to be 1.2. Now, just going back to the original function, just to get some helpful things in graphing x and y intercepts. If we factored out a 2x squared from the original function, that's going to be x plus 2. This is original function now. To find zeros, we're going to have a 0 then at 0 and a 0 at -2. Now this particular 0 has multiplicity, which means it bounces. So it's going to bounce at 0 and cross here at -2. Now plotting some of the other points we found some relative extrema at -4/3. That's -1 1/3, comma 2.04. So -1 1/3, 2.04 there. That's a relative max. Relative min is 0, 0. We also had an inflection point at -2/3, comma 1.2. So -2/3, comma 1.2. That right there. That's our inflection point. This is a cubic function. Which has a typical graph shape like that. So there's our maximum, minimum, point of inflection right there. We've labeled and found everything that they're asking for. I believe we are done with that one.